In late 2025, a research team at the European Space Agency's Earth Observation Center in Frascati, Italy, published the results of 11 years of magnetic field data from the Swarm satellite constellation. What they found was straightforward and a little unsettling. The South Atlantic Anomaly, the region of unusually weak magnetic field over the South Atlantic Ocean, first identified in the 19th century, had grown by an area nearly half the size of continental Europe in just over a decade. A new lobe, developing southwest of Africa, had begun weakening even faster than the rest of the anomaly after 2020. The North Magnetic Pole, meanwhile, was officially closer to Siberia than to Canada, a position it had not been in for centuries, and the field's overall strength was lower than at any point in the last several thousand years of measurable Earth history. None of this means civilization is ending. The shield is not collapsing. Life has survived every previous magnetic transition in Earth's 4 billion-year history, and the fossil record from those transitions shows no mass extinctions, no climate catastrophes, nothing that qualifies as a planetary disaster. But something is changing inside Earth's core, on human timescales, faster than the standard models predicted. And, for the first time in the 4 billion-year history of life on this planet, we have the instruments to watch it happen in real time. The European Space Agency's Earth Observation Center, a research team, is looking at two maps on a screen. The maps are identical in shape, projections of Earth, centered on the South Atlantic Ocean. The first map shows the magnetic field strength in 2014. The second shows it in 2025. The two maps do not look the same. The weak zone, the region where the magnetic field is measurably thinner than anywhere else on the planet, has grown, not slightly, not by a margin that requires careful measurement to detect. It has grown by an area nearly half the size of continental Europe. In 11 years, Chris Finlay, professor of geomagnetism at the Technical University of Denmark, is the lead author of the study that produced these maps. His team has spent years analyzing data from the European Space Agency's Swarm satellite constellation. 3 satellites in coordinated orbits, circling Earth continuously, measuring the magnetic field with a precision no ground-based instrument has ever matched. He looks at the comparison. He looks at the African coast on the right side of the screen, where a new lobe of the anomaly, a region of even faster weakening, has been developing since 2020. A region the standard models did not predict, he says, in a quote that will appear in the ESA's official release. The South Atlantic Anomaly is not just a single block. It's changing differently towards Africa than it is near South America. There's something special happening in this region that is causing the field to weaken in a more intense way. The statement is measured. It is also, in its careful way, an acknowledgement that the planetary system that has been protecting life on this planet for billions of years is doing something the standard models did not predict. Not collapsing, not disappearing, but changing, faster than expected, in directions that nobody quite anticipated, and doing it right now, in real time, on human timescales. The North Magnetic Pole, which spent centuries sitting quietly over northern Canada, has been racing towards Siberia. In the late 1990s and early 2000s, it was moving at speeds of up to 60 kilometers per year, fast enough that the World Magnetic Model, the global reference system that underpins GPS, aviation, and maritime navigation, had to be updated ahead of its normal 5-year schedule. That out-of-cycle update came in early 2019. The pole has since slowed. As of the most recent World Magnetic Model release in late 2024, it is moving at closer to 35 kilometers per year, still well above its historical pace, but a noticeable deceleration from the peak speeds of 2 decades ago. The pole has, however, crossed the international date line. It is now officially closer to Siberia than to the Canadian Arctic, where it spent most of the 20th century. The field's overall strength, measured globally, has been declining for centuries, approximately 9% weaker than it was 2 centuries ago when systematic measurement began, lower, by some estimates, than at any point in the last several thousand years of measurable Earth history. And the acceleration of the South Atlantic Anomaly since 2020 is not slowing down. Something is changing inside Earth's core. It has been changing for decades, and we have only recently developed the instruments to watch it clearly enough to understand how fast. This is not a distant future scenario. The satellites measuring it are in orbit right now. The changes they are recording are happening in real time. And the gap between what the standard models predicted and what the data actually shows has been quietly growing for years, noticed by scientists, documented in peer-reviewed papers, and missed by almost everyone else. The magnetic field is not about to vanish, but it is doing something, and that something deserves a careful, honest answer. This video is about Earth's magnetic field. It is the invisible shield that makes this planet livable, generated deep inside the Earth by convection currents in the liquid iron outer core. It extends far into space as the magnetosphere, deflecting the constant stream of charged particles flowing outward from the Sun, protecting the atmosphere from being slowly stripped away, and keeping radiation at the surface low enough for complex life to exist. Without it, Earth would slowly become Mars. The field has been measurably weakening for at least 2 centuries. The South Atlantic Anomaly has been expanding steadily since at least 2014, and has accelerated in part of its region since 2020. The North Magnetic Pole has been moving towards Siberia at rates unprecedented in 4 centuries of continuous measurement, forcing the World Magnetic Model, the reference system underlying GPS and modern navigation, to be updated ahead of schedule once already, with the regular 5-year update arriving in late 2024. None of this is speculation. These are measurements from satellites, from observatories, from a global network of magnetic sensors that has been running for over a century. The question is what these measurements mean. Are we watching normal variation, the kind of fluctuation the field goes through on geological timescales, with no implications beyond the interesting? Are we watching the early stages of a geomagnetic excursion, a partial, temporary weakening like the Lachem's event approximately 41,000 years ago, when the field weakened dramatically for centuries before recovering? Or are we watching something that has not happened in 780,000 years? The beginning of a full geomagnetic reversal, in which the north and south magnetic poles swap positions over the course of thousands of years, while the field goes through a period of complex weakness. This is not just about a weakening shield. This is about the one planetary system that we have been taking completely for granted for the entire history of human civilization, and what happens when that system starts changing faster than our models predicted. By the end of this video, you will understand exactly what is happening to the magnetic field, where the changes are coming from, what the real risks are as opposed to the sensationalized ones, and what the science currently says about how this ends. So, what is actually happening inside Earth's core right now? Why has the South Atlantic Anomaly expanded by nearly half the size of continental Europe in just 11 years? Why has the North Magnetic Pole been moving so fast that GPS infrastructure had to be updated early? How weak has the field gotten, and how weak could it get? What does a geomagnetic excursion actually look like up close, and have modern humans lived through one before? What is the difference between the sensationalist version of this story and the real one? And what does the science actually say about whether a full pole reversal, an event that has happened hundreds of times in Earth's history, but never once during the era of modern technology, could be beginning right now? This is not a doomsday video. The magnetic field is not going to disappear. The planet is not about to become uninhabitable. Life has survived every pole reversal in Earth's 4 billion-year history, and the fossil record from previous reversals shows no mass extinctions, no dramatic climate collapses, nothing that qualifies as a catastrophe for life. But this is also not a video that dismisses the real changes that are happening. Something is genuinely occurring inside Earth's core. The field is genuinely weaker than it has been at any point in the last several thousand years. The changes are genuinely happening faster than the standard models predicted, and the gap between the sensationalist version, civilization is ending, the shield is collapsing, we are all at risk, and the dismissive version, nothing to worry about, completely normal, the media is overreacting, is exactly where the most interesting science lies. Stay with me, the truth is more interesting than either extreme. Quick pause. If you're enjoying this kind of slow, careful storytelling, hit subscribe. Galaxy Pulse goes deep on stories others rush through. Now, back to the magnetic field. To understand why a weakening magnetic field matters, what it actually protects us from, and what changes when it weakens, we need to start from the beginning. Most people know the magnetic field exists. Fewer people know where it comes from, how it works, and how extraordinary it is that it has worked as reliably as it has for as long as it has. Because the story of Earth's magnetic field is, at its foundation, the story of something that should not be as stable as it has been. A self-sustaining electromagnetic process, running in a liquid iron ocean nearly 3,000 kilometers below our feet, keeping itself going through a feedback loop that is so complex that the world's best supercomputers can only approximate it. That story begins not at the surface of the planet, but nearly 3,000 kilometers beneath it. The Earth is not solid all the way through. Most people learn this in school. But the structure of the planet's interior is worth revisiting, because everything that follows depends on it. From the surface down, the layers go like this. The crust, the thin, solid shell we live on, ranging from 5 kilometers thick under the oceans to 70 kilometers thick under mountain ranges. Below that, the mantle, approximately 2,900 kilometers of hot, slow-moving rock, so hot it flows over geological timescales, but so dense and pressurized that it behaves like a solid in most short-term contexts. And below that, in the innermost regions of the planet, the core. The core has two layers. The outer core, approximately 2,200 kilometers of liquid iron-nickel alloy at temperatures of several thousand degrees Celsius, and the inner core, a solid iron-nickel sphere about 1,200 kilometers in radius, under pressures so extreme that even at those temperatures, the iron remains solid. The magnetic field comes from the outer core. Here is how. The outer core is liquid, and it is in constant convective motion. Heat from the inner core rises. Cooler, denser material sinks. The whole mass churns, continuously, driven by the temperature difference between the hot inner core and the cooler boundary where the core meets the mantle. Now, add one more ingredient. Iron conducts electricity. A moving conductor in a magnetic field generates an electrical current. An electrical current generates a magnetic field. And that magnetic field, in turn, influences the motion of the conducting liquid, which generates more current, which generates more magnetic field. The system feeds itself. It is called the geodynamo, and it has been running more or less continuously for billions of years. Let that sink in for a moment, because it is genuinely remarkable. The magnetic field is not generated by a giant permanent magnet in the Earth's core. At the temperatures that exist at the core mantle boundary, roughly 3,500 degrees Celsius, iron is far above its Curie temperature, the point at which permanent magnetism disappears. Permanent magnetism cannot exist at those temperatures. What exists, instead, is a continuously self-sustaining electromagnetic process, powered by the slow decay of radioactive elements and the solidification of the inner core, that has been running essentially without stopping for most of Earth's history. The field extends from this process upward through the mantle, through the crust, through the atmosphere, and out into space. At the surface, it is relatively weak, weaker than a typical refrigerator magnet. But it extends for tens of thousands of kilometers into space, and across that distance, it does something no magnet on your kitchen appliance can do. It turns aside the solar wind. The solar wind is a constant outflow of charged particles, protons, electrons, helium nuclei, streaming outward from the sun at hundreds of kilometers per second. Without the magnetosphere to deflect it, the solar wind would gradually erode Earth's atmosphere. It would do to Earth what it has already done to Mars, strip away most of the atmosphere over billions of years, leaving behind a cold, thin, radiation-bathed surface where complex life cannot exist. The magnetosphere turns it aside. The charged particles, encountering the magnetic field, are deflected. They flow around the Earth, most of them following the field lines into the polar regions where they produce the auroras. The atmosphere stays in place. Life continues. This has been happening for the entire history of complex life on Earth. Every multicellular organism that has ever lived, every dinosaur, every mammal, every fish, every insect, every plant, has lived inside this shield, entirely unaware of it. Now consider this. For the first time in that 4 billion year history, we have instruments sensitive enough to watch the shield change in real time. And what those instruments are showing us is that the field is doing something it has always done, changing, wandering, weakening in some places, strengthening in others, but doing it right now, on timescales that are fast enough for us to measure year by year. The change is not sudden, but it is real, and it is measurable, and it has been accelerating in places. Under a stable geodynamo, here is what the magnetic field should look like. A roughly dipolar structure, 2 poles, a consistent overall field strength, slow and predictable changes over decades and centuries as the convection patterns in the outer core slowly evolve. The poles would wander, but slowly, a few kilometers per year, following patterns that could be modeled and predicted. The field strength might vary, but within a range that centuries of measurement would establish as normal, small fluctuations, no dramatic trends. That is, more or less, what the field looked like through most of the 20th century. What it looks like now is different. The North Magnetic Pole moved from northern Canada towards Siberia at rates of up to 60 kilometers per year during the late 1990s and early 2000s. For context, over the previous century, the pole had moved an average of about 10 to 15 kilometers per year. The acceleration that began in the 1990s represented the fastest sustained polar movement in the 400-year record of magnetic measurements. The pole has since slowed to roughly 35 kilometers per year, still significantly faster than its historical pace, but the largest deceleration ever measured. The pole has now crossed the international date line and is officially closer to Siberia than to the Canadian Arctic. Why it sped up and then slowed is a question scientists are still working on. The South Atlantic Anomaly has expanded by an area nearly half the size of continental Europe in just over a decade, according to the most recent SWARM mission data. A new lobe of the anomaly, developing southwest of Africa, has been weakening faster than the rest of the region since 2020, in a direction and at a rate that the standard models did not predict. And the global field strength, the average intensity of the field measured across the entire planet, has been weakening for at least 2 centuries, approximately 9% weaker than it was when systematic measurement began. Other parts of the field are doing the opposite. Over Siberia, A region of unusually strong magnetic field has been growing by an area roughly the size of Greenland, according to the most recent swarm analysis. Over Canada, a region of historically strong field has been shrinking by an area roughly the size of India. The gap between what the simple models said should happen and what the data is actually showing has been widening. The field is not collapsing, but it is changing, and in places, it is changing faster than the standard models suggested it would. The story of the South Atlantic Anomaly begins, officially, in the 19th century. In the 1800s, as global navigation expanded and magnetic surveys became more systematic, compass measurements from ships crossing the South Atlantic began returning unusual values. The magnetic field in that region was weaker than expected. Not dramatically, not enough to make a compass stop working, but measurably, consistently weaker than the surrounding ocean. Surveyors noted it, navigators noted it. The anomaly was catalogued and mapped, and it was treated, for most of the next century, as a curiosity, a quirk of the field's geometry. In the space age, the anomaly acquired practical importance. As satellites began orbiting the Earth in the 1960s and 70s, engineers discovered that spacecraft passing over the South Atlantic were encountering unexpectedly high levels of radiation. The weak field in the region allowed the inner Van Allen radiation belt, a donut-shaped zone of high-energy, charged particles trapped by the magnetic field, to dip closer to Earth's surface than anywhere else on the planet. Satellites in low Earth orbit were punching through this radiation belt once per orbit when crossing the South Atlantic. The effects were real and measurable. Electronics glitched, memory was corrupted, instruments went into safe mode. The International Space Station schedules its extravehicular activities to avoid the anomaly when possible. The Hubble Space Telescope's instruments shut down briefly each time it passes through. The South Atlantic Anomaly was a known engineering problem. It was being dealt with. It was not, by itself, a scientific alarm. Then, in 2013, the European Space Agency launched the Swarm constellation. Swarm consisted of 3 satellites in carefully designed orbits, 2 flying side by side at lower altitude, the third in a higher, polar orbit. Together, they were designed to separate the different sources of Earth's magnetic field: the core, the mantle, the crust, the ionosphere, the magnetosphere, and measure each one with a precision no previous instrument had achieved. The mission was originally planned for 4 years. It is still operating in 2026, more than a decade after launch, with the data from its extended mission representing the most detailed continuous record of Earth's magnetic field ever assembled. What the swarm data showed, published in multiple studies, but most comprehensively in the Finlay et al. Paper of late 2025, core field changes from 11 years of swarm satellite observations in physics of the Earth and planetary interiors, was this: the South Atlantic Anomaly had expanded steadily from 2014 to 2025. Not by a small margin, by an area nearly half the size of continental Europe. The weak zone had moved westward, grown in area, and deepened in places. And since 2020, something new had appeared. A region of the Atlantic Ocean southwest of Africa, on the eastern edge of the anomaly, had begun weakening faster than the rest. A new lobe, developing separately from the main anomaly structure, with its own internal dynamics. Finlay put it plainly in the ESA release. The South Atlantic Anomaly is not just a single block. It's changing differently towards Africa than it is near South America. There's something special happening in this region that is causing the field to weaken in a more intense way. The implication of that statement, understated as it is significant. The anomaly is not simply expanding uniformly. It is developing internal complexity. Different parts of it are changing at different rates, in different directions, driven by different processes in the core below. The simple picture, a single weak zone, slowly expanding, is no longer adequate to describe what the data shows. And running in parallel to the South Atlantic story, the North Magnetic Pole was telling its own unusual tale. The pole had been wandering for as long as it had been tracked. That is normal. What was not normal was the speed. Through the 1990s and into the early 2000s, the pole accelerated dramatically. It had been moving at roughly 10 to 15 kilometers per year through most of the 20th century. By the early 2000s, it was moving at 50 to 60 kilometers per year, so fast that the World Magnetic Model, the global reference system updated every 5 years by a joint British-American scientific program and used by every GPS device on the planet, had to be updated ahead of schedule in early 2019, when its predictions drifted outside acceptable accuracy limits for navigation purposes. That was the first out-of-cycle update in the model's history. The regular 5-year update arrived in December of 2024, the World Magnetic Model 2025 release. By that point, the pole had decelerated significantly to around 35 kilometers per year. Still well above pre-1990 averages, but a noticeable slowdown. The pole has now crossed the international date line into the Eastern Hemisphere, a position it has not been in for many centuries. Both the South Atlantic story and the North Pole story are manifestations of the same underlying reality. The convection patterns in the Earth's liquid outer core are changing, and those changes are affecting the field we can measure at the surface. Before we go further, let us slow down for a moment and make sure the science here is clear, because the rest of this story depends on understanding a few things, and they are not difficult. They have just been obscured, in most coverage of this topic, by either too much technical jargon or too much apocalyptic framing. Think of it this way. Imagine Earth's outer core as a pot of very thick, very hot liquid on a stove. The stove, the inner core, is the heat source, extremely hot at the center, cooler toward the edges. As the liquid near the stove heats up, it rises. As the liquid near the top cools slightly, it sinks. The whole pot churns continuously in slow convective rolls. Now, this liquid is an iron alloy. Iron conducts electricity, and a moving conductor in a magnetic field generates an electrical current. That current generates a magnetic field. That field influences the flow of the liquid. That flow generates more current. The feedback loop sustains itself. This is the geodynamo, the self-sustaining electromagnetic engine inside the Earth. What the swarm data is telling us is that the churning patterns in that pot of liquid have changed, not catastrophically, not suddenly, but measurably, directionally, and in ways that are affecting the field we can detect at the surface. There are 3 things you need to understand to follow what comes next. The first is what the South Atlantic Anomaly actually is, physically. The anomaly is not simply a place where the field is weak for mysterious reasons. It has a specific physical cause. Deep beneath the South Atlantic, near the core-mantle boundary, there is a patch of reverse polarity magnetic field, an area where the local field direction is opposite to the dominant global direction. This reversed patch creates a local cancellation of the main field, producing the weak zone we observe at the surface. The patch has been there for a long time, at least several centuries, based on historical records, but it has been growing. The second is what the pole's wandering means, mechanically. The magnetic poles are not fixed geographic locations. They are the surface expression of the underlying convection pattern in the outer core. As the convection patterns shift, as different regions of the core strengthen or weaken in their contribution to the global field, the poles follow. The North Pole's movement towards Siberia reflects a weakening of the field contribution from the Canadian sector of the core and a relative strengthening from the Siberian sector. It is a symptom of reorganization in the fluid dynamics thousands of kilometers below. The third is the scale of the weakening. 9% in 2 centuries sounds modest, but consider the context. The field was already in a weaker phase historically, and the weakening is not uniform. In the South Atlantic region, the field is locally much weaker than the global average. The SAA is not a 9% weak zone. It is a region where the field is weakened by a much larger factor, enough that the Van Allen radiation belt dips to altitudes where satellites operate. These are not abstractions, these are measurements, so here is where the stakes start to rise. If the SAA is expanding, and if the North Pole has been moving faster than at any point in recorded history, and if the field's overall strength is lower than at any point in millennia, then we have to ask, honestly, what this actually means for us. Because the magnetic field is not just a navigational convenience. It is a planetary life support system, and the changes being measured right now are real, measurable, and fast enough to matter on human timescales. Let us be specific. Satellites and spacecraft are already affected by the SAA. As the anomaly expands, more satellites pass through it more frequently. Satellites in low Earth orbit are designed with radiation hardening to handle the SAA. But that hardening is calibrated to a specific radiation environment. As the SAA expands and deepens, the radiation environment changes, satellite lifetimes shorten. Hardware failures become more common. The cost of operating in low Earth orbit increases. This is not hypothetical. It is a documented, ongoing engineering challenge that the satellite industry is actively tracking. In the era of satellite megaconstellations, Starlink, OneWeb, Amazon's Kuiper, and their successors, involving thousands of satellites in low Earth orbit, the SAA's expansion is not an academic concern. GPS and navigation are affected by the magnetic North Pole's movement. The World Magnetic Model is a critical piece of infrastructure. Every GPS device on the planet uses it. Every aircraft navigation system uses it. Every ship autopilot uses it. The fact that the pole moved fast enough to force an early update of the WMM in 2019 was not a minor administrative event. It was a sign that the field was changing faster than the 5-year update cycle of the model was designed to accommodate. Power grids are potentially vulnerable in a different way. Solar storms, eruptions of charged particles from the sun, can drive geomagnetically induced currents through long conductor systems like power lines and pipelines. A stronger magnetic field provides more protection against these events. A weaker field provides less. During periods of lowest field strength, the risk from large solar storms would be significantly higher than it is today. Animals that navigate by the magnetic field, sea turtles, migratory birds, whales, monarch butterflies, could be disoriented if the field weakens significantly or if the poles shift dramatically. This is a real biological concern, not a trivial one, for species whose entire reproductive strategy depends on magnetic navigation. These are the real stakes, not the end of civilization, not the vanishing of the shield, not the apocalyptic framing that circulates in viral articles every time a new SAA paper is published. Real, specific, documented, ongoing consequences of a real, measured, ongoing change in a planetary system that we have been taking for granted for the entire history of our species. The swarm data tells us what is happening at the surface. It tells us where the field is weak, where it is strengthening, how fast the anomaly is growing, how fast the pole is moving. But to understand why, we have to go deeper. Because the South Atlantic Anomaly, the wandering North Pole, the weakening global field, none of these are surface phenomena. They are projections onto the surface of something happening nearly 3,000 kilometers below us, in the liquid iron outer core of the planet. and what the latest research is revealing about what is down there, about the structure of the core-mantle boundary beneath the South Atlantic, and about what is driving the unusual dynamics in the outer core, is something that would have been impossible to know a decade ago. It changes the picture considerably. The South Atlantic Anomaly does not exist because the South Atlantic Ocean is special. It exists because of what is happening directly beneath it, 3,000 kilometers down, at the boundary between the mantle and the outer core. That boundary, the core-mantle boundary, or CMB, is one of the most dramatic physical interfaces inside the planet. Above it is the solid, slow-moving rock of the lower mantle. Below it is the liquid, churning iron of the outer core. The temperature jump across this boundary is enormous. The materials on either side are fundamentally different in composition, density, and behavior. And the boundary is not smooth. Seismic studies, analyses of how earthquake waves travel through the Earth's interior, have been revealing, for the past 2 decades, that the core-mantle boundary has significant topography. There are regions where the boundary appears to be rougher, where the composition of the lowermost mantle is different, and where the behavior of the liquid core just below the boundary seems to be influenced by the structure above it. One of the most unusual of these regions sits beneath the South Atlantic and Africa. Seismologists have identified an enormous structure in the lowermost mantle in this region, described in the technical literature as a large, low-shear velocity province. A region where seismic waves travel significantly slower than in surrounding rock. This anomalous region spans thousands of kilometers. Its exact composition and origin are debated, but the most common interpretations involve unusually hot material, partially molten material, or material with different chemical composition than the surrounding mantle. Whatever it is, it appears to be affecting the liquid iron just below it. The hypothesis that has gained the most traction in the geophysics literature is this: the anomalous structure of the core-mantle boundary in this region creates unusual convection patterns in the outer core directly beneath it. Those convection patterns have driven the formation and growth of a reversed polarity patch, a region where the local magnetic field direction is opposite to the global dominant direction. That reversed patch, when projected upward through the mantle and crust to the surface, produces the South Atlantic Anomaly. The patch is not new. Historical magnetic data, going back several centuries, shows evidence of this reversed region. Ancient lava flows and sediment cores preserve a record of the field direction stretching back thousands of years, and the signatures are consistent with a long-standing reversed region beneath the South Atlantic that has been slowly growing. But slowly growing has, in recent decades, become something faster. The swarm data shows that the SAA has been expanding at an accelerating rate in places. The new lobe, developing southwest of Africa, the one that appeared after 2020, suggests that the reversed polarity patch in the core is developing additional complexity. It is not simply getting bigger, it is developing internal structure, with different regions evolving at different rates and in different directions. This is significant for several reasons. It means that the simple picture of a single reversed polarity patch is probably inadequate. The region beneath the South Atlantic may contain multiple distinct features, driven by multiple processes, interacting with each other in ways that the current generation of models has not fully captured. It also means that the swarm satellites, the most precise magnetic field monitors ever deployed, are now, for the first time in history, giving us the ability to watch the core change in something close to real time. Not in geological time, not in centuries, in years. The North Pole story connects to the same underlying dynamics. As the field geometry beneath the surface evolves, the magnetic North Pole, which is drawn toward the region of the Earth's surface above the strongest area of the field, moves with it. The weakening in the Canadian sector and the relative strengthening in the Siberian sector, both documented in the swarm data, are driving the pole's migration. All of these changes originate from the same source. Something in the convection patterns of the outer core is reorganizing. We can see it from space. We can measure it year by year. And we are only beginning to understand what is driving it. The magnetic field has reversed before, many times, hundreds of times. In the last 83 million years alone, there have been more than 180 documented reversals. On average, one approximately every few 100,000 years, though the intervals have varied enormously, from as short as 10,000 years to as long as tens of millions of years. We know this because of a remarkable accident of geology. When lava erupts and cools, the magnetic minerals in it, mostly magnetite and hematite, align with whatever direction the magnetic field is pointing at the time. When the rock solidifies, that alignment is frozen in place. The rock becomes, in effect, a permanent record of the field direction at the moment of cooling. For the last 2 centuries, geologists have been reading this record. They have sampled ancient lavas from volcanic islands and ocean ridges. They have analyzed deep-sea sediment cores, which record the direction of the field in the magnetic minerals that slowly settled out of the water column over millions of years. They have studied the distinctive pattern of magnetic stripes on the ocean floor, the magnetic anomalies that provided some of the most compelling evidence for plate tectonics in the 1960s. From all of this, the geomagnetic reversal chronology has been assembled. The last full reversal, the Brun-Smatayama reversal, occurred approximately 780,000 years ago. Since then, the field has been in what geophysicists call the Brun's Chron, a period of consistent polarity, with magnetic north roughly where it is today. That 780,000 years is a long time. The average interval between reversals over the past few tens of millions of years has been somewhere in the range of several 100,000 years. We are, by that measure, somewhat overdue. This is a fact that appears in papers, in popular science, and in the sensationalist versions of this story, sometimes with appropriate context and sometimes without. The important caveat is that overdue does not mean imminent. Reversals do not happen on a schedule. The intervals between them are statistically irregular. The geological record shows some intervals as short as 10,000 years and some as long as tens of millions. The fact that 780,000 years have passed since the last reversal tells us very little, by itself, about when the next one will occur. But the field is weaker than the long-term average. And that fact, combined with the overdueness, is part of why serious scientists are watching the current changes more carefully than they would if both factors were absent. There is also a category of events that sits between normal variation and full reversal. They are called geomagnetic excursions. An excursion is a short-lived, incomplete flip. An event in which the field weakens dramatically and the poles wander far from their usual positions, but the field then recovers to something close to its previous configuration, rather than completing a full reversal to the opposite polarity. The best studied example is the Lachemse event, approximately 41,000 years ago. During the Lachemse event, the global magnetic field weakened to a small fraction of its current strength. The poles shifted dramatically, in some records, appearing to reverse temporarily before swinging back. The event lasted on the order of centuries. Then, the field recovered and resumed its previous polarity. Modern humans lived through this event. Anatomically modern Homo sapiens and Neanderthals were both alive during the Lachemse excursion. The fossil and archaeological records show no mass extinction. There is no clear global climate catastrophe. The radiocarbon record from this period shows elevated cosmic ray flux at the surface, the signature of a weakened field letting more particles through. but the biological consequences appear to have been limited. Recent studies of peat layers and other geological archives have traced several Holocene magnetic fluctuations as well, including a marked weakening a few thousand years ago, linked to historical sightings of auroras at unusually low latitudes and to isotopic evidence of increased cosmic radiation in contemporary geological layers. The events were real. Their consequences for human civilizations at the time were apparently limited. The geological record, in short, provides genuine reassurance on one crucial point. Life survives excursions, life survives full reversals, the planet continues, the atmosphere continues, complex ecosystems continue. But there is a caveat to this reassurance that the geological record cannot address. The Lachemps event occurred 41,000 years ago. Human civilization, in its modern form, did not exist. There were no satellites, no GPS, no global electrical grid, no navigation systems depending on precise magnetic field models, no megaconstellations of satellites in low Earth orbit, engineered to specific radiation tolerances. Every previous excursion and reversal in the geological record occurred on a planet without any of these things. The question of what an excursion would mean for a civilization with these dependencies is a question that the geological record cannot answer, because no such civilization existed during any previous event. Let us be specific about what a significantly weaker magnetic field actually means for the world as it exists today. Not in metaphorical terms, in engineering terms, in economic terms, in terms of documented, peer-reviewed risk assessments that insurance companies, space agencies, and power grid operators take seriously. The first category of risk is satellites and spacecraft. The South Atlantic Anomaly is already causing operational problems for the satellite industry. Satellites in low Earth orbit are designed with radiation hardening to handle the anomaly, but that hardening is calibrated to a specific radiation environment. As the SAA expands westward, and as the new African lobe develops, more satellites encounter higher radiation during more passes. The effect is cumulative over a satellite's operational lifetime: accelerated degradation of electronics, increased rates of single-event upsets, greater power system degradation. The International Space Station is already protected by extra shielding in sections most exposed to the SAA, and astronauts are tracked for radiation dose during passes through the region. As low Earth orbit becomes more populated, with megaconstellations eventually placing tens of thousands of satellites in LEO, the aggregate exposure to SAA radiation will increase. Satellites designed to specific radiation tolerances may need redesign if the SAA continues expanding at its current rate. The second category is GPS and navigation infrastructure. The World Magnetic Model is the global reference standard for magnetic declination, the angular difference between true north and magnetic north, used by every navigation system on the planet. Airlines, militaries, shipping companies, hikers with compasses, and the mapping software on every smartphone all depend on this model being accurate. When the magnetic North Pole's acceleration forced an early WMM update in early 2019, it was the first unscheduled update in the model's history. The 5-year update cycle had been sufficient for decades. The pole's behavior in the 2000s made it insufficient. The next regular 5-year update, the WMM 225, released in December of 2024, incorporated the slowdown that has since occurred. If the pole's behavior continues to be unpredictable, navigation infrastructure will require continuous adaptation rather than purely scheduled updates. This is manageable, but it represents a real and ongoing cost. The third category, and arguably the most economically significant, is power grid vulnerability. Solar storms, Coronal mass ejections from the Sun drive geomagnetically induced currents through long conductor systems, power lines, gas pipelines, railway lines, submarine cables. These currents can overload transformers, cause protective systems to trip, and in severe cases damage equipment that is difficult and slow to replace. The 1989 Quebec blackout is the benchmark modern case. A moderately large solar storm, nothing like the Carrington event of 1859, knocked out power to millions of people across the northeastern United States and Canada for hours. Transformers were damaged. The economic cost was substantial. The Carrington event itself was significantly more powerful. Risk assessments published by Lloyd's of London and other insurance institutions have estimated that a Carrington equivalent event hitting the modern power grid could cause economic losses in the trillions of dollars in North America alone, with recovery times of months to years for the most affected regions. Here is the connection to the magnetic field. The magnetosphere is Earth's first line of defense against solar storms. A stronger field deflects more solar particles. A weaker field allows more to penetrate. A field that is weakening and whose structure is becoming more complex as the poles wander and the SAA expands, provides less and less consistent protection. During the Lachamps event, when the field dropped to a small fraction of its current strength, cosmic ray and charged particle flux at the Earth's surface was significantly elevated. Radiocarbon records show it clearly. A modern power grid operating during an equivalent event, struck by a Carrington-scale storm, would face a much higher GIC burden than the same storm would produce today. The fourth category is biological. Multiple species navigate by the magnetic field. Sea turtles detect magnetic signatures at their birth beaches and return to them decades later. Humpback whales follow magnetic contours during migrations spanning thousands of kilometers. Monarch butterflies use a light-dependent magnetic compass during their migration from Canada to Mexico. Multiple species of migratory birds use the field for directional orientation. None of these animals use only the magnetic field for navigation. They integrate magnetic signals with visual cues, solar position, star maps, and other sensory inputs. But magnetic disruption has been documented to cause navigational errors in controlled conditions. For species whose reproductive success depends on successfully completing migrations, sustained disruption of the field could have population-level effects. None of this is apocalyptic. None of it suggests extinction-level consequences. But it is all real, documented, and ongoing. And all of it becomes more significant if the weakening continues or accelerates in the coming decades. There are three serious interpretations of what the current magnetic field behavior actually means. They sit on a ladder, conservative at the bottom, bold at the top. Each one is held by some segment of the geophysics community. Each one has supporting evidence and real weaknesses, and the choice between them will not be resolved by any single paper or measurement. It will be resolved, slowly, over the next generation of observations. The conservative interpretation is that we are watching normal variation. In this view, the current weakening, the SAA expansion, and the North Pole movement are within the range of natural geomagnetic variation. The field has been in weaker phases before. The rate of change, while fast by historical standards, is not unprecedented in the longer geological record. The 9% weakening in 2 centuries, the SAA expansion in 11 years. These are notable, but not necessarily outside the envelope of what a dynamically active geodynamo can produce without going into a reversal or excursion. The supporting evidence comes from multiple sources, including Finlay's own statements that the study did not find any sign of an impending magnetic field reversal. The field today is weaker than in recent centuries, but stronger than it was during the Lachamps event. There have been periods of magnetic variability in the Holocene that were comparable in amplitude to what we are currently seeing, and none of them led to a reversal. The weakness of this view, in the current context, is the development of the new African lobe of the SAA, which was not predicted by standard models. The fact that the anomaly is developing internal structure, behaving differently in different regions, suggests a level of complexity in the underlying core dynamics that the simple normal variation framing does not fully capture. This is still the majority view in the geophysics community, but it is held with more qualification than it was a decade ago. The moderate interpretation is that a geomagnetic excursion may be possible in the future. In this view, the combination of a weakening global field, a rapidly expanding SAA with novel internal structure, and a long-term migration of the North Pole is broadly consistent with what the early stages of an excursion might look like. If one were to begin, not a full reversal, an event in which the field weakens dramatically, the poles wander far from their usual positions, and then the field recovers. This interpretation draws on the structure of previous excursions, particularly the Lachamps event. The weakness is that the precursor signatures of excursions are not well characterized. We have never had instruments like SWARM during the lead-up to an excursion. We do not know what the field looked like in detail in the decades and centuries before the Lachamps event began. The similarity between the current field behavior and what a pre-excursion field might look like is suggestive but not confirmatory. This is a respected but minority view among geophysicists studying the modern field. The bold interpretation is that the changes could, over very long timescales, be the early signature of a process that eventually leads to a full reversal. This is the view that gets the most popular attention and the least scientific support. Some mathematical modeling work on the predictability of magnetic field reversals has suggested that the present configuration of the field may be consistent with the very early stages of a multimillennial transition. These are minority statements made within larger papers, and they are framed cautiously by the researchers themselves. The weakness is that reversals have no reliable, well-characterized precursor signatures. The field has been weakening for 2 centuries without reversing. The current behavior is consistent with a reversal beginning. It is also consistent with many scenarios that do not include a reversal. The current scientific consensus is cautious. Scientists are watching. They are collecting data. They are refining models. They are not declaring that a reversal is imminent, but they are also not dismissing the possibility outright. Here is what is worth saying before we leave the theoretical landscape and move to the implications. The magnetic field has been changing since the day it was born, billions of years ago. It has reversed, recovered, wandered, strengthened, and weakened countless times while life continued to evolve. The only thing that is genuinely new is that we can now watch it in real time. The SWARM satellites, the World Magnetic Model updates, the seismic imaging of the core mantle boundary, all of this is unprecedented. We are seeing things that previous generations of scientists could only infer from ancient rocks. That watching is not evidence of catastrophe. It is the most honest kind of scientific attention, paying close enough attention to see what is actually happening without deciding in advance what it means. The magnetic field is not collapsing, but it is doing something, and what it is doing is more interesting, more complex, and more worthy of attention than either the sensationalist or the dismissive version of this story suggests. After everything we have seen, the SWARM data, the deep core dynamics, the geological record, the real technology risks, the 3 competing interpretations, the question is no longer whether the magnetic field is changing. It is. The question is what that change actually means for a civilization that now depends on this field in ways that no previous form of life ever has. And here is where the story takes a turn that most coverage of this topic has never gotten to. Here is the strange thing about how the Earth's magnetic field has been covered in popular media. The story tends to come out in one of two forms. The first form is the alarm version. Every time a new study on the SAA is published, a wave of articles appears declaring that the shield is collapsing, that civilization is at risk, that a magnetic reversal is imminent. The language escalates with each cycle, faster than expected, could happen any day, NASA is worried. The actual science is compressed into a few sentences, stripped of context, and surrounded by language designed to produce fear. The second form is the dismissal version. Science journalists and researchers, responding to the alarm cycle, publish corrections emphasizing that everything is fine, that this is normal variation, that the field has been doing this for billions of years, that there is no reason to worry. This version is more scientifically accurate in many respects, but it sometimes dismisses things that are genuinely worth paying attention to. Both versions miss what the technical literature actually says. Let me give you specific examples. The most recent comprehensive study, the Finlay et al. Paper from late 2025, representing 11 years of swarm satellite data, received some mainstream coverage, but far less than it deserved given its scientific significance. The paper documented the expansion of the SAA by an area half the size of continental Europe and identified a new, faster weakening lobe developing southwest of Africa since 2020. These are significant findings. A second example, the fact that the World Magnetic Model had to be updated ahead of schedule in 2019 was widely reported, but most coverage presented it as a curiosity. The North Pole is drifting, GPS needs a tweak. Interesting. The deeper implication, that the pole was moving so fast that the Global Navigation Reference System could not keep up with its normal cycle, was rarely drawn out. A third example, the documented satellite and power grid risks associated with the SAA's expansion are taken seriously by the space industry, by power grid operators, and by insurance companies. Lloyd's of London has published risk assessments of space weather impacts on modern infrastructure. NASA has active programs studying the SAA precisely because it affects spacecraft operations. The ESA extended the swarm mission, in part, because the data it provides is operationally relevant for satellite design and operations. These are not the actions of organizations that dismiss the changes as irrelevant, but the gap between what these organizations are actually doing, monitoring, adapting, designing more resilient systems, and the popular coverage of the topic is substantial. A fourth example, the internal complexity of the SAA. The fact that it is not a single uniform weak zone, but a dynamic structure with distinct internal lobes, behaving differently in different regions, is a genuinely new scientific finding. The pre-2020 picture of the SAA was simpler, a weak zone, expanding westward, driven by a single reversed polarity patch in the core. The post-2020 data shows something more complex. Multiple lobes, different rates of change in different regions, behavior that the standard models did not predict. This complexity matters because it changes what we can say about the future trajectory of the anomaly. A single, simple structure expanding uniformly is relatively easy to model. A complex, multi-lobed structure with different internal dynamics is harder to predict. And there is the philosophical question that almost never appears in popular coverage. We are, right now, the first generation in the 4-billion-year history of life on this planet to be able to watch the magnetic field change in real time. Every generation before us saw a static field, changing so slowly that the magnetic North Pole's position had barely moved within a human lifetime. We see a field that is visibly moving on decadal timescales, that is developing new structure, that is changing the relationship between our technology and the planet beneath us. That is new. That is remarkable, and how we respond to it, whether we panic, dismiss, or pay careful attention, matters. In the time since the publication of the Finlay et al. Paper, the picture has continued to develop. Several parallel streams of research are converging on an increasingly detailed, if still incomplete, understanding of what is happening inside Earth's core, and what the surface observations actually mean. The first development is in seismic imaging of the continental boundary, the large, low shear velocity province beneath the South Atlantic and Africa. The anomalous region in the lowermost mantle that appears to be connected to the SAA's behavior is being studied with increasing sophistication using global seismograph networks. As more seismometers are deployed across South America, Africa, and the islands of the South Atlantic, the resolution of seismic images of the continental boundary in this region is improving. Recent results suggest that the low-velocity province has more internal structure than previously recognized. The connection between this and the SAA's growing internal complexity at the surface is suggestive but not yet proven. The research to confirm or refute the connection is ongoing. The second development is in the modeling of the geodynamo. The last decade has seen significant advances in the computational power available for geodynamo simulations. Models that were too computationally expensive to run a decade ago are now feasible. These high-resolution simulations are producing new insights into how the outer core's convection patterns relate to the surface field, and specifically into how reversed polarity patches like the one beneath the South Atlantic form, grow, and evolve. Some of these simulations have produced behavior reminiscent of what the swarm satellites are observing: a growing reversed polarity patch, associated weakening of the global dipole, and pole movement in a consistent direction. These simulations do not predict a reversal in any specific timeframe, but they suggest that the current field configuration is physically plausible within the framework of geodynamo behavior, and that the timescales on which the current changes are occurring are not inconsistent with what the models produce. The third development is the World Magnetic Model 2025 release. The update released in December of 2024, bringing the model into effect through 2029, captured the most recent position of the magnetic North Pole. It is now firmly in the Eastern Hemisphere, continuing its long drift toward Siberia, but at a significantly slower pace than during the peak years of the late 1990s and early 2000s, the largest deceleration in pole speed ever measured. A high-resolution variant of the model, the WMMHR 225, was released alongside the standard version, providing much greater spatial detail for satellite-based systems and next-generation autonomous vehicles requiring sub-kilometer accuracy in magnetic heading. The next regular update will arrive in 2029 or 2030. The comparison between the 2025 and 2030 models will provide another data point on whether the changes are continuing, stabilizing, or shifting again. The fourth development is operational. The satellite industry is adapting. Several satellite operators have begun publishing studies of how SAA expansion is affecting their fleet operations, and designing next-generation satellites with updated radiation tolerance specifications based on projected SAA growth. Power grid operators in regions most exposed to geomagnetically induced currents, particularly in northern latitudes where GIC risk is highest, are investing in monitoring and protection systems. The North American Electric Reliability Corporation has updated its standards for transformer protection against GIC events. European power grid operators have similar programs underway. None of this is panic. All of it is sensible preparation, driven by real risk assessments, based on real data. The world is adapting to a changing magnetic field, quietly, technically, without dramatic announcements, in ways that most popular coverage has not captured. The next decade of geomagnetic monitoring will be shaped by what we are learning from the Swarm mission right now. That is true regardless of whether the current changes represent normal variation or the early stages of something more significant. The first thing to understand is that monitoring is improving. The Swarm constellation is scheduled to continue operating into the next decade. ESA mission manager Anja Strum has confirmed that all satellites remain healthy, and that the coming solar minimum will allow even clearer observation of Earth's internal field. A follow-on mission is being planned to maintain the continuity of precise, satellite-based magnetic field monitoring. Ground-based magnetic observatories, of which there are roughly 200 worldwide, providing a continuous record going back in some cases over a century, are being upgraded and extended, particularly in the data-sparse southern hemisphere. The combination of ground observatories and satellite measurements provides a multi-resolution picture of the field that is richer than at any previous point in history. The second thing to understand is that space weather resilience is becoming an active engineering priority. The convergence of a weakening magnetic field with the rapid expansion of low Earth orbit satellite infrastructure is being taken seriously by engineers, policymakers, and risk analysts. The fact that thousands of new satellites are being deployed each year, precisely during a period when the SAA is expanding, is creating a genuine engineering challenge. The next generation of LEO satellites is being designed with this challenge in mind. Power grid hardening against geomagnetically induced currents is advancing in multiple countries. The economic case for GIC protection, given the potential losses from a Carrington-level event during a period of reduced field strength, is compelling enough that the investment is proceeding. The third thing to understand is the longer scientific arc. Understanding what is happening inside Earth's core is one of the fundamental open problems in planetary science. The outer core is, by definition, inaccessible. We cannot drill into it, we cannot sample it. We can only infer its behavior from the magnetic field it generates, and the seismic waves that pass through it. The Swarm mission has made extraordinary progress in reading those inferences, but there is much more to understand. The next decade will see advances in core-mantle boundary imaging, higher resolution geodynamo simulations, and potentially the first real-time observation of significant geomagnetic events in human history. The geological record tells us what excursions and reversals look like in retrospect. We have never watched one happen, even in the most accelerated scenarios that scientists are taking seriously. The changes we are observing now will play out over decades and centuries, not years. That is enough time to adapt, to prepare, and to understand what is happening before it happens. The field has been changing for billions of years. For the first time, we are watching closely enough to see it change in real time. What we do with that watching, how we build more resilient satellites, smarter power grids, better early warning systems for solar storms, will determine whether the changes ahead are a crisis or simply a challenge that a technologically capable civilization was ready to meet. And here is what makes all of this truly remarkable. The magnetic field has been changing, constantly, measurably, for the entire 4 billion year history of this planet. It reversed, it wandered, it weakened and recovered. Life not only survived these changes, it evolved through them. The first complex animals, the first vertebrates, the first mammals, the first primates, all of them emerged on a planet whose magnetic field was in constant motion, occasionally going through major transitions, and occasionally going through reversals that took thousands of years to complete. The field was never perfectly stable, We just thought it was, because we have only been measuring it carefully for about 200 years. And, in those 200 years, it has been relatively quiet by geological standards, enough that the assumption of stability seemed reasonable. What the Swarm mission has done is not reveal a new crisis. It has revealed how dynamic a system we have been living inside, without knowing it, for the entire span of human civilization. Let that sit for a moment. Everything you have ever done, every navigation, every satellite phone call, every GPS route, every solar storm that curved harmlessly around the planet instead of frying the power grid. All of it happened inside a magnetic field that was already changing, already weakening, already moving in ways that, had we been watching carefully, we would have noticed decades earlier. The Swarm satellites gave us the first real view of this dynamic system, and what they showed us, in 11 years of continuous data, was a field in motion in ways that are faster than average in places, in directions that simple models did not predict, and with implications for satellite infrastructure, navigation systems, and power grid resilience that deserve serious, sustained attention. Not panic, not dismissal, attention. The field is not collapsing, but it is doing something. And what it is doing is, in a strange way, proof of something remarkable. That we live on a planet whose interior is alive, whose dynamics reach from the core to the edge of space, and whose behavior we are, for the first time in the history of life on this planet, capable of monitoring in real time. That capability is extraordinary. It is the result of decades of scientific work, engineering ingenuity, and international cooperation. And what we do with that capability, whether we build the resilient infrastructure, the smarter satellites, the better early warning systems, will define whether the changes in Earth's magnetic field over the next century are remembered as a crisis we were unprepared for, or a challenge that a careful, attentive civilization was ready to meet. The universe is always doing something. We are only just getting good enough at watching, but there is one more piece to this story. Because Earth is not the only planet in our solar system to have experienced a magnetic field collapse. There is another planet, once similar to Earth in many ways, once warm, once wet, once potentially habitable, whose magnetic field did not weaken. It died, completely. And when it did, the solar winds stripped away the atmosphere, the water evaporated into space, and a planet that may once have hosted life became the cold, radiation-bathed desert we call Mars today. The story of what happened to Mars's magnetic field, and why, is not just a cautionary tale. It is a direct comparison to what Earth's field is doing right now, and the differences between the two stories are more interesting than the similarities. That is a story for next time. Tonight, we did not just learn about a weakening magnetic field. We watched what happens when an invisible planetary system, one that has been quietly protecting every living thing on this planet for 4 billion years, one that we have never had to consciously think about because it has always been there, starts changing in ways we can finally see. We saw a team of scientists at the ESA looking at two maps side by side, 11 years apart, and seeing a weak zone that had grown by half the size of a continent. We saw the North Magnetic Pole crossing into the Eastern Hemisphere after centuries of sitting over the Canadian Arctic, fast enough during its peak movement that the navigation systems of the entire planet needed early recalibration. We saw the geological record laid down in ancient volcanic rock and deep ocean sediment, telling us that the field has done this before, hundreds of times, and that life survived every time. We saw the specific, real technology risks that a weakening field creates for the satellite networks and power grids and navigation systems that modern civilization depends on. And we saw, in the gap between the sensationalist version and the dismissive version of this story, the actual truth. Something real is happening inside Earth's core. It is measurable. It is ongoing. It is faster, in places, than simple models predicted. And for the first time in the 4 billion-year history of this planet, we have the instruments to watch it. And yet, even now, the fundamental questions remain open. We do not know whether the acceleration of the SAA's new African lobe since 2020 will continue, stabilize, or reverse. The swarm data is the best we have ever had, but it covers only 11 years of a process that operates on timescales of centuries and millennia. We do not know what is specifically causing the unusual structure of the core-mantle boundary beneath the South Atlantic and Africa, or how it is driving the reversed polarity patch in the outer core. The seismic imaging is improving, but the core remains inaccessible. We do not know whether the current field behavior is a precursor to a geomagnetic excursion, the beginning of a slow process that could eventually lead to something larger, or simply a period of enhanced variability that will eventually stabilize. The precursor signatures are not well characterized enough to distinguish between these scenarios, and we do not know how quickly the technology sector, satellite design, power grid protection, navigation systems, can adapt if the weakening continues or accelerates beyond current projections. These questions are genuinely open. The next decade of satellite data, seismic imaging, and geodynamo modeling will narrow the uncertainty, but it will not eliminate it. There are a few things worth taking from this story that go beyond Earth's magnetic field. The first is that the most important planetary systems are often the most invisible. The magnetic field has protected life on this planet for billions of years. We have taken it for granted because we could not see it changing. Now we can. The first step toward responsible engagement with a changing system is simply being willing to look. The second is that the gap between sensationalism and dismissal is where the most interesting science lies. The field is genuinely changing. It is not collapsing. Both the alarmist framing and the dismissive framing fail to describe what is actually happening, and both fail to give the real story the attention it deserves. The third is that watching is not the same as understanding. The swarm satellites give us unprecedented data, but the models of why the field behaves the way it does are still incomplete. Every generation of scientists has learned that observation and explanation are different stages of the same process, and the humility to acknowledge the gap between them is a scientific virtue. The fourth is that resilience is not the same as panic. The real response to a weakening magnetic field is not fear. It is better satellites, smarter power grids, early warning systems for solar storms, updated navigation models. Engineering, not catastrophizing. The world is already doing this, quietly. It deserves more attention than the viral alarm cycles it usually gets instead. And the fifth is this: every generation studies the universe with better instruments than the last. What looks like a crisis may, in part, be the experience of finally being able to see something that was always happening. The field was always changing. We just could not watch before, so I want to leave you with a few questions tonight. What does it mean to live on a planet whose most important protective system is invisible to you? How much of our sense of stability comes from things we cannot see and have never had to think about? When you look at the gap between the sensationalist version of this story and the real one, what does that gap tell you about how we, as a culture, process information about slow, complex, planetary scale changes? Why do we need either the alarm or the dismissal? Why is the honest middle so hard to hold onto? And what would it actually mean to take the magnetic field seriously, not as a source of fear, but as something worth understanding, monitoring, and building our technology to accommodate? Sit with those for a moment. They are bigger than the magnetic field. If this story stayed with you, tell me in the comments, which moment was the one that pulled you in? Was it the swarm satellite data showing the SAA growing by half the size of Europe? the North Magnetic Pole, after centuries over Canada, now officially closer to Siberia. The geological record showing that life survived every previous reversal. Or the realization at the end that we are the first generation of humans who can actually watch the magnetic field change in real time, and that what we do with that information matters. I want to know. And if you want more stories like this, real planetary science, told without the hype and without the dismissal, subscribe to Galaxy Pulse. We go beyond the headlines every single time. I will see you in the next one. For 4 billion years, an invisible shield has been wrapping itself around this planet, turning away the solar wind, holding the atmosphere in place, making everything we call life possible. It was never still. It was always moving, always changing, always doing something we were not watching closely enough to see. Now, for the first time, we are watching. And what we see, if we are honest about it, is both more ordinary and more astonishing than we were prepared for.